Okay, so let's start. So in this week's content for the robotics course, I will cover the content that has been discussed in week two, and that would be helpful in the assignments that is due on 5th of February. So I will first describe what is the agenda for today. So the agenda for today includes first discussing about rotation matrices, second discussing about homogeneous transformations, and third discussing about the DH parameters. Basically, knowing about these three topics will help us to describe the kinematics and subsequently dynamics of these multi-linked robots that we want to analyze. Right, so this will lead us to the kinematics, and kinematics will finally be used in arriving at the dynamics, which is our final goal. All right, so getting started with the agenda for today. First is rotation matrices. Now I'll quickly describe the uh, the theoretical concepts of rotation matrices using the lecture slides as well. Right, and I will also solve some questions in regards to these rotation matrices to further highlight the concepts. So this is the diagram which I want to refer to, which has been discussed in the lectures. Basically, we have a rigid body B, and we have frames assigned to that body. One is frame A, which has the origin OA, right? And frames are denoted by this uh, uppercase alphabet inside curly brackets. And there is another frame B, which is at a different orientation compared to A. However, both their origins are coincident. So OA and OB are the same point, but the B frame is oriented differently than the A frame. Right. Now, what we want to achieve here is that we want to obtain a description of frame B with respect to frame A. Right. So that is our goal. How we proceed to do that is by first describing the unit vectors, that is the vector along each of the three axes of frame B, that is xb hat, yb hat, and zb hat, in terms of unit vectors of frame A. Right, so let me just rewrite the same thing here, and I will follow the same notation. So that is the description of the x-axis of frame B, the unit vector along the x-axis of frame B in frame A. That is what this notation means, right? And this is the description in terms of the unit vectors of frame A. So that is R11 XA hat plus R12 YA hat plus R13 ZA hat. Similarly, for the y-axis, it's R21 XA hat plus R22 YA hat and R23 ZA hat. And finally, the z-axis of frame B represented in terms of the unit vectors of frame A can be written as R31 R32 YA hat plus R33 ZA hat. All right. Now, these numbers that we have written in before these unit vectors, this Rij, they are called as direction cosines. Why direction cosines? Because they give us the angle that the unit vector, let's say the unit vector of x of frame B, how much angle does it make with the unit vector of along x of frame A, right? So this is, as we know, if we take dot product of two unit vectors, then the resulting thing is the angle between the unit vectors because the magnitude of the unit vector is 1. So these two quantities are 1. And finally, we get the cosine of the uh, angle between the two unit vectors. So Rij, they are termed as the direction cosines. And for instance, R11 is cos A x b hat, comma x a hat, right? And so on. So finally, what we do is that we can write these three equations in a more like compact form by using the matrix multiplication notation. So if I take this as a vector and make another vector here, right? Then if we multiply these two, we get the same thing, right? So similarly, we can write for y b a and z b a. So finally, what we get is that, right? So this is the finally we get what is called as the rotation matrix, and that is basically collecting all these direction cosines. This is the rotation matrix. And what purpose does it serve? It describes the orientation of frame B, which is the rotated frame, with respect to orient frame A. Right. So our matrix completely describes all three coordinate axes of B with respect to A. That is, this matrix, this rotation matrix, gives us the orientation of rigid body B in the frame A, right? So this is one very common and widely used approach to describe orientation of a rigid body. Any questions till here? Okay. So now this matrix is a very special matrix, right? It has few properties that are key and are utilized in all the subsequent derivations that we will do, right? So first thing is that the columns of this matrix are they are unit vectors, and hence the matrix is orthonormal because these columns are also mutually uh, perpendicular, right? So xb times dot product with yb, or yb dotted with zb, or zb dotted with xb, they all give 0, right? So there are three independent vectors, right? And this this rotation matrix in this form has 9 parameters, but due to these two equations on the norm of these unit vectors and the mutual orthogonality of these unit vectors, they impose 6 constraints, and thus only 3 independent parameters are left, right? So 9 parameters were there initially, minus 3 due to unit norm, and minus 6 due to, wait, 6 minus 3 due to mutual orthogonal. So the remaining is 3. So orientation can be parametrized by 3 independent parameters. Okay. Now, a few other important properties are, the first most common is and most useful is that determinant of R should be unity. So determinant of R should be unity, right? And the other thing is that the transpose of the rotation matrix is also its inverse. That is true for any orthonormal matrix. So R transpose is equal to R inverse. Okay, so R transpose equal to R inverse, right? And there are few other things which we will discuss when I describe an example, right? But briefly, this is about rotations, and then we discuss about the elementary rotations, right? So the elementary rotations are rotations about the either just the x-axis, the y-axis, or the z-axis. Right? So Rx, not plus minus one, it should be always plus one, right? So determinant is always plus one, not it cannot be minus one. Okay, did I clear your doubt? Yeah. Okay. So once we know all these properties, we discuss elementary rotations. So basically, whenever we will tackle problems having successive rotations about different axes, each of those rotations would be about the x, y, z axis of any frame, and we would should be able to write the rotation matrix about the x, about the y, about the z axis. So I'll just describe those first. So that is right. So first about the x-axis. So since the rotation is about the x-axis, this unit vector remains the same, right? And then here it will be cos theta minus sine theta, cos theta. Just one notational remark is that we will be writing cos theta, sine theta multiple times while discussing rotations. So we will write sine theta as s theta and cos theta as c theta. So this is a very standard notation which you might have already come across. Right, so this is Rx, Ry, again Ry, the rotation is about y-axis, so that remains the same. And it's c theta, s theta minus s theta, c theta, right? And Rz is c theta minus s theta, 0, 0, 0, 1, s theta, and c theta. Right. So these are the three elementary rotations, which is also described here, or the simple rotations. Now, once we uh, have these simple rotations, then we can basically go towards successive rotations. Successive rotations, or in other words, a sequence of rotations. Okay, so basically what we have is that now we are rotating a frame. These rotations are not clockwise, these rotations are anti-clockwise because we are taking the anti-clockwise direction as the positive direction. Okay, yeah, please keep asking questions whenever you feel any doubt. So in successive rotations, what we have is that we are rotating, there are more than one rotations, as the name suggests, and it can be any number of rotations, but the idea remains the same. So we can basically understand these concepts using, let's say, two or three rotations, but that can be extended with exactly the same thing can be extended for any arbitrary number of rotations, n number of rotations, right? So what we have is that uh, in this example, we have frame B that is coincident with frame A first. Then there is first rotation that is relative to A, which means that uh, we are rotating about any one of the axis of frame A, right? And after doing that rotation, we arrive at frame B1. Now, the second rotation is relative to frame B1, which means that we are rotating the second time about any one of the axis of frame B1, be it X, Y, Z, but they are not the axis of frame A, but they are axis of frame B1, right? And after that rotation, we arrive at frame B. Now, these two rotations that we do, uh, what we want to achieve then is that we should be able to describe this succession of rotations in one single rotation matrix, right? And that is called the resultant rotation. So the rotation from B to A, or the description of frame B in frame A, can be written as description of frame B in frame B1, and then description of frame B1 in frame A, right? You can also understand it as that we are post multiplying the rotation matrices. So I'll just write the same thing here. So we have, and that is A R B1 and then B1 B R. Just give me a second. All right. So this is RB, right? So this is the first rotation, and this is the second rotation, right? ARB1. This is about any, let's say, any of the axis, let's say XA, at any of the axis of the frame A, and let's say by theta 1, right? And then the second rotation is about any of the axis of frame B1, right? So it would be, let's say, Y of frame B1, and about, and by certain angle theta 2, right? So this is what is mentioned here. And this can be basically extended to n number of rotations. And the most important point to note here is that the mathematical reason is also there and the physical reason is also there. So matrix multiplication is generally non-commutative or non-commutative, right? So this means that our B B1 our B1A is not equal to our B1A R just A B1 B1 B. Yeah, yeah. So this is B1 B and then R B1 A. No, it is A B1. Yeah. Basically, you are multiplying these two matrices in the other order. So first, this is first and then second, and here this is first and this is second, right? And these generally do not give the same rotation matrices, and which means that order of rotation is very important. I can't emphasize this enough. It's very, very important. Okay. Now, at this point, what I will do is that I will start discussing a question, and while solving that question and understanding that question, we will cover the remaining concepts that are relevant for rotation matrices, and whatever we just saw, we will verify those things as well. And this problem is related to exactly related to what we just now discussed, that is uh, successive rotations, and then basically showing that if we change the order of rotations, then we do not physically, it does not mean the same rotation, right? So let me first describe the problem setup. Okay. So I will take a couple of minutes to draw the figure that is required in the question, and I would suggest that you also draw with me. All right. So this is our problem setup. So we have a rectangular plate. Now what we have is this. This is the frame A, and we have this other frame that is attached. Right, that is attached to the right. So frame B is attached to the rectangular plate. Right. So frame B is attached to the plate, and frame A is the world or the global or the what we call as the inertial frame. Right. So now what we will do is I will write down the sequence of rotations. Right. So sequence of rotations. So first rotation is with respect to what we just wrote here mathematically. First rotation is with respect to frame A, and it's can be written as a rotation matrix about XA, right, and about and by 90 degrees, right. And the second rotation is with respect to B1, and that is about uh, the z-axis of B1, and that is also 90 degrees. Okay, so these two rotations we are taking, and this will be enough to highlight all the important concepts that we want to cover. Right. So this is the first rotation about the x-axis of the global frame or the fixed frame, and this is the second rotation about the z-axis of the rotated frame. So z-axis of the rotated frame, and this is the x-axis of the fixed frame. Okay. Now, the first thing that we'll do. Any doubts in the problem setup? Anyone? Why we have taken z over here? There is no specific reason, Pankaj. Uh, I'm just describing, just taking an example. So that could well have been anything else, right? Just that in my example that I'm giving, I'm taking a rotation about the z-axis and the x-axis. So it's not that these specific rotations hold any special meaning. It's just that I have chosen these numbers to highlight the concepts that I want to. Okay, so yeah, so let me just the first thing that we'll do is the equivalent final rotation matrix, right? So I will also figuratively draw these two rotations so that everything is very clear. And I will also change the notation here because I'm using B and B1. So this is YB, ZB, XB is the B frame. This is OB, and this is XA, ZA, A, this is OA, right? So again, drawing the world frame. This is the world frame. The first rotation is about this, right? So after this rotation, the plate would be, you can imagine something like this. We have rotated, no, we have rotated by 90 degree. So it would be something like this. Right. The plane was first in the XZ plane. The plate was first in the XZ plane. Now it has rotated 90 degrees. So it's now in the XY plane. Right. So you can imagine this plate is now 90-degree rotated. So it's standing up like this. Right. So this is the plate. And the axis, the frame that was fixed to the uh, plate, right? So basically, when plate moves, that frame also moves. When plate changes its rotation, the frame also changes its rotation, its orientation, right? So the new The orientation of the body fixed frame would be now something like this. Like you can just simply try to imagine with me, right? So since we rotated about x, the x-axis would remain the same. The x-axis would remain the same, and then the y-axis basically comes this side. This is yb1, and the z-axis goes down, further down here, right? And here this x-axis is overlapping, right? So x cross y z. We verify that also. So this b1, the subscript b1 is the intermediate frame. Okay, so we have frame A, then we have a rotation R X A 90 degrees, right? And we get frame B1. Then we have another rotation R about Z B1, and that is 90 degree, and that is frame B that we want to describe, right? So after first rotation, the scenario looks something like this. Okay. Now I will also draw the second rotation also. Again, drawing the world frame first. Please let me know if anyone has any doubts and questions regarding this problem that we are discussing. Okay, in so this is the world frame. Now the second rotation happens about the ZB1 axis. So this is the ZB1 axis, and we have to rotate anti-clockwise around that, right? So this is ZB1, and since the rotation is about this axis itself, ZB2 will also remain, or ZB will also remain the same. ZB will also remain the same, right? And if you imagine if you are rotating about like this, then the X of this B frame would come here, and the Y would go this side. Okay, please try to keep up and imagining with me. And the plate would somewhere be here. Somewhere not, like it must be here. Right, so this is about like this rotation about the ZB1 axis. This is our XA about 90 degree, and this is our ZB1 90 degree. Okay, so this is the final orientation of the rectangular plate after these two rotations. Right, so I think the physical picture is clear. Now we will evaluate it mathematically. That the frame, the B frame, right, that is the final frame attached to the plate. So what is the orientation of the B frame in the A frame? That's our first question, right? So let's start answering that. So as we saw above, that this can be broken down as individual simple rotation. So in this case, the first would be R X A, and then and here would be R Z B1. Hmm. Now, if you remember the simple rotation or the elementary rotations, then this should be not very difficult to write. So it's for x, it should be 1, 0, 0, 0, 0, and then cos theta minus sine theta, cos theta. So cos 90 is 0, so this is 0, minus sine theta 0. Right, and on this side we have ZB1 and rotate about again 90 degree. So it's like 0, 0. Again cos theta, that is 0, minus sine theta 0. Right, and if you multiply this, we get, I have done this, so what I will do before, once again, so this is 0, minus 1, 0, so I have done this multiplication beforehand so that I can write it quickly. Any doubts still here? Okay, so now what we have is we have a single matrix representing the orientation of frame B in frame A. And the good thing is that uh, we took this step-by-step rotation approach and we just had to multiply them to get the final rotation matrix. All right. Now we can verify the properties that we have seen above, right? So first is that R transpose times R is identity, right? So then you can see that R transpose would be 0, 0, 1 minus 1, 0, 0. This would be 0, minus 1, 0, and this should be 0, minus 1, 0. Now, if you multiply this, we get 1, 0, 0, 0, 1, 0. And this is what? This is an identity matrix. Okay, so this is verified. Now we had that determinant of R is always plus 1. So if you take the determinant of this matrix, where R is so taking determinant of this, we get 0 times 0 minus 0 minus minus 1, 0 plus 1 plus 0, 0 minus 0. Right, so this becomes 1. And this you can try with any rotation matrix that you find. The determinant is always 1. And if that's not the case, that means something is wrong with the rotation matrix. Okay, so having got this out of the way, uh, what other properties do we want to check for? Okay. So now we saw that the combined rotation, the combined rotation matrix is 0, minus 1, 0, 0, 0, minus 1, and 1, 0, 0. Now I'll write two formulae and I will tell you the significance of that. So what are these two things? So first let me describe the idea here. Right. So the idea is very simple yet very powerful. Right. It says that any successive or sequence of rotations can be represented by an equivalent axis and a single rotation about that axis, right? So if we moved around x, then we moved around z, right, and we finally reached here. So the idea is to find an axis about which we can directly rotate the uh, object by some angle, again given by that. So that is the axis angle corresponding to the equivalent rotation. So this is equivalent axis angle notation. Now, if we know the matrix R, we can very easily calculate theta and k. So k is the axis about which that single rotation has to take place, and theta is the angle value. Now let's calculate theta and k for this case. So our case, cos inverse trace of r is 0, so 0 minus 1 by 2, and k is actually 1, actually minus 1. Right. K is a unit vector, remember that. That's why we are using a hat. And that root 3 is basically serving the purpose of normalizing the, if in case an unscaled. Now theta is 2 pi by 3, that is 120 degrees. And this is, yeah, this is as it is. Right. So if you rotate about this axis 1 minus 1 1, and if you rotate by 2 pi by 3 radians, then in one single rotation we can arrive from this lying down position to this standing vertical on z axis position. Okay. Now what we'll do is we'll also verify the, now what we'll discuss is called the Rodriguez formula. So Rodriguez formula. So what does this say is that the rotation matrix, and if I know the axis and the angle, the equivalent axis and the angle, without specifically knowing each successive rotation, then this can be written as, and here n is the skew symmetric matrix of n hat, right? So if n hat is equal to nx, ny, nz, so the n is So this will be okay. So in our case, nx is equal to 1 by root 3, ny equal to minus 1 by root 3, and nz is equal to 1 by root 3 once again. Okay, so in this case, the n matrix would be, and 1 by root 3 is 0.5774. Minus 0.5774, 0. Minus 5744.5. Hmm. So this is our basically the uh, n matrix, right? And if we use theta is equal to 120 degrees and n equal to this, and then use this Rodriguez formula, then we will get the rotation matrix for this equivalent angle and axis. So let's verify that this rotation matrix comes out to be same as what we manually calculated using by just multiplying the subsequent rotations. So I is the identity matrix. So this will be 1 0 0 0 1 0 0 0 1. Then sine theta is 120 degree. So sine theta is root 3 by 2, right? And n is 0 minus 1 1 minus 1 0 1 minus 1. Yeah, 0 minus 1, and this is also minus 1 1 0 minus 1 minus this is plus 1. This is 1 1 1, and this is 0, right? This is the n matrix, and I have again written 1 by root 3 outside only so that I can just cancel this out, right? And plus 1 minus cos theta, that is 1 minus, and cos 120 is minus half, so 1 minus minus half, right? And then n square, the same matrix ka square, right? So Just to save time, I can show you here that theta is 2 pi by 3, and then I calculate the rotation matrix, that is identity plus sine theta into n plus 1 minus cos theta into n square. And this is what I get, that is 0 minus 1 0, 0 0 minus 1, and 1 0 0, which is exactly the same that we got. So what we get is 0 minus 1 0, 0 0 minus 1, and 1 0 0. So this is same. Any questions still here? Please keep uh, solving this and drawing these diagrams as I draw, right? Because just looking at the image, it might be difficult to understand later. So now what we have established is that any sequence of rotations can be represented by a single rotation about a specific axis, right? And how do we calculate that axis that we saw here is that first we should know the rotation matrix that we want to work with, like for which we want to calculate the equivalent axis and angle. So in this case, that is this rotation matrix. And then we use these two expressions, which I will just encircle. Right. And then once we got the equivalent axis and the angle, we then again used the Rodriguez formula to compute the rotation matrix, and it as it is expected, we get the same rotation matrix once again. Okay, so the key takeaways from here, from the discussion up till now, I will summarize about rotation matrices now so that we can move on to the next topic in the agenda. So the key things here are that rotation matrices describe the orientation of a rigid body with respect to a certain frame, right? So it is a frame dependent quantity. It depends with respect to which frame we are describing the orientation. Then, then what we have is uh, we have few properties, few interesting and useful properties about rotation matrices. That is, the determinant of rotation matrix is always plus one. The inverse of the rotation matrix is its transpose. That is, rotation matrix is orthonormal. Each of the columns of the rotation matrix are orthogonal to each other, and they are also unit vectors. Then we saw the expressions for the elementary rotations about the x, y, and the z axis. And then we have the successive rotations thing, in which we saw that how do we compose a sequence of rotations into a one single rotation matrix. And here we noted that uh, if we flip or change the order of rotation, then it is generally not the same. And I will just highlight this point using this example also. So here we rotated first about the x-axis and then about the z-axis of the rotated frame, and we arrive here. Now just imagine with me, if I rotate first about the z-axis. So if I rotate about the z-axis, right, then the plate would be somewhere here. So just as a side example, So if I would have rotated about the z-axis, then after first rotation, the plate would have been here, right? And the x-axis, the x-axis would have been towards this side, right? And if we would have rotated after that about that x-axis 90 degree, then the plate would have been like this, right? So you see that the end configuration of the plate is very different from what we get in this sequence to what we get in the reverse sequence, right? So this highlights that uh, in 3D rotations, the sequence of rotations matters. Then we derived the composite rotation matrix and we verified these few properties that indeed rotation matrix is orthonormal matrix and determinant is +1. And finally, we used a very useful tool of finding the equivalent axis and angle. So the rotation matrix, this rotation matrix can be represented as an equivalent rotation about this k axis by angle theta. So this is the axis angle representation. And we saw how to calculate that angle and that axis. And then once we know that angle and axis, we can use the Rodriguez formula to compute the rotation matrix, right? Okay, so now let's move on to the second part of the agenda, that is homogeneous transformations. So the purpose of homogeneous transformations is to describe rotation and translation together. Okay, so I will refer to the lecture slides for this purpose. Yeah, so the transformation matrix is a 4 cross 4 matrix and it describes combined translation and rotation, right? So there is this rotation matrix part, that is the orientation of frame B with respect to frame A, and this OB describes the translation of origin of frame B with respect to origin of frame A. So now the origin of these two frames are not anymore coincident necessarily, right? So there is also like a translation and then a rotation, both combined. And together we make this matrix a 4 cross 4 matrix and we denote it by the alphabet T. So this matrix takes position vector described in frame B to its corresponding description in frame A. So this matrix D A B is represented as R A B 0 0 1, and this is A O B. And this is the translation part. This is the rotation part. Okay. And what we write is we are writing basically this expression that PA is OB plus R A, B, B, B. Okay, that is a point PB. We first rotate it into frame A, then we translate it to get the description of point P in frame A, right? And the inverse of this transformation, inverse of this transformation is given by TAB inverse, and that is the inverse of rotation matrix is its transpose. So here is the slightly tricky part, that this is minus RAB transpose and AOB, and this is the same, right? So we have this inverse of rotation, and then we are basically converting this back to frame B, and then subtracting that translation. And then again, successive transformations can be concatenated in the same way as we concatenated the rotation matrices. And this n successive transformations can be represented like this. All right, so let's do a quick, again, I will use an example problem to walk you through the usage of the homogeneous transformation. So let me just pull up the question, and I will pull up the question from the book by Craig. And yeah, so the question says develop a general formula to obtain the transformation from B to A, where starting from initial coincidence B is rotated by theta about k. K is again that general axis that we discussed, where k passes through the point PA, not through the origin of A in general. Right. So first let's draw the picture of this setting. So we have the frame A. Then we have an axis K, and K passes through a point P, right? And we are rotating about this by angle theta, right? And this point P is not like on the origin of frame A, it's not OA, right? And basically, this frame B to begin with is coincident. However, the frame B to begin with is coincident with frame A, right? So this is frame B and this is OB. So let me just put it once again. So we have two frames. We have frame A, the base frame, and we have frame B. Frame A and B are initially coincident, right? And their origins are also the same. Now frame B is rotated about an axis k cap, which is basically passing not through the origin of these two frames, but a different point P, right? And the angle of rotation is theta. Okay. So what we see here is that there is also an element of translation involved in this because in order to apply the usual rotation matrix about an axis by a given angle formula, we would need that the k passes through the origin of that frame, right? So what we will do is that we can draw an intermediate frame here, right? And so basically this is, let's say, this is frame B. First we translate this frame to here. This is B1, right? Then we rotate this frame by theta, right? To get, let's say, frame B2, and then we translate again back to here and bring that rotated frame here to get the final frame, that is B dash. So there are three steps. First is translation of P, translation by a vector P, then rotation of theta about K, and third is reverse translation of P. Okay, so I hope this is clear. Okay, so the significance of Rodriguez formula is that if I describe, so basically it gives me much more freedom in describing rotations. So let's say if I want to describe the rotation about one single axis. So basically, if I, let's say, have 10 rotations, right? If I have sequence of 10 rotations, or let's say not 10, let's say 3 rotations, because uh, I can basically make any two frames coincident in the 3D space using 3 rotations. Okay, so let's say I have 3 rotations. Then in order to describe the the rotation which takes me from frame A to frame B, rather than describing three axes and three angles, I get one equivalent axis and one equivalent angle. So it's a more like a compact and a dense form of describing rotations. However, the thing is that it might be a little bit not intuitive to imagine, because it's like there is one vector which is not along like x y z, it's some non-trivial vector about which we are rotating by some non-trivial angle, but mathematically we have seen that it does reach us to the same orientation. So it's just ease of description, that rather than specifying three axis angle pairs, we can specify just one axis angle pair. I hope that's uh, clear now. Okay, so in this case, what we have to do is first we have to translate, then rotate about the k-axis, and then again reverse back the translation, because finally we want the frame of B to be coincident with frame of A. Okay, so now how do we write these transformations mathematically? So this is like translation along vector, unit vector along P, and the magnitude of translation is the magnitude of that vector P. Then we have rotation, and rotation is about axis K and by angle theta. And then again translation, but this time in reverse, and then again by same magnitude. Okay, so these are the three things we uh, that we basically use to describe this transformation. Okay, and then we can basically write the matrix representation of each of these and multiply them. Okay, so let's just write each of them individually. So this is identity here because it's pure translation. So the rotation part is identity, and here it is px, py, pz, and 1. Then the reverse case, we have minus a p, pa, and here it is I, and then minus px, py, pz. This is 0, 0, 1. Right. So these two parts are clear. And now we have the this rotation about k theta, this part. And this is basically a big matrix, right, which whose expression is not very trivial to write as well. So I'll just put a picture of that expression, and that can be basically used to understand. So I will again refer to the book and use the general expression for a rotation of theta about an axis k. All right. So this is the expression, that is basically here what is I will describe what are these things. So the vector k is represented as kx, ky, kz, right? V theta is 1 minus c theta, and c theta and s theta, as we know, they are like cos theta, and s theta is like sine theta. Okay, so if we put the values of all these things and then we multiply, then we get the final transformation matrix, right? So the final transformation matrix would be something like this, where this part is r k theta, and here we have some terms qx, let's say qx, qy, qz, right? And what you can do is you can on your own do this multiplication and find out. What I will do is just uh, I will paste the answer from the textbook here, right? Right. So these are the expressions for qx, qy, and qz. And finally, this transformation matrix is represented like this. So what we take from here is that how we can combine a general rotation and rotation about an arbitrary axis with our basically our uh, translations, right? And give this and get this combined rotation and translation in form of a homogeneous transformation. Any doubts here? Anyone? Okay. So now we are on the last part of today's agenda. That is, I will solve a problem describing the DH parameters. So for a quick recap of DH parameters, I will refer to the slides and yeah. So DH parameters are basically used to describe the link transformations. So basically, they gave us the parameters which can be used to write the transformation matrices from one link to another link and write them easily. Okay, so we have a system in which multiple links are there and joints are there, and first we have to attach frames, and there is a specific convention for attaching frames, right? So for coordinate system I minus 1, that is frame I minus 1, we attach the zth frame z axis along the joint axis. So for revolute joint, that is the axis of rotation. For prismatic joint, that is along the axis of translation. Then the the x axis is chosen to be the common perpendicular between the two consecutive z axis. Right, so that is the x. And once x and z are defined, y can be found out by doing right hand rule cross product. Okay, so for coordinate system I, zi is the along joint axis I, xi is the common perpendicular between zi and zi plus 1. Okay, and the origin of I, OI is the point of intersection of line along xi and the line along zi. So where xi and zi intersect, that is the origin of the frame I. Right. Now there are four DH parameters, namely twist angle, the link length, the link offset, and the rotation angle. So these are the four quantities which basically we find out when we are writing the DH parameters for a system. So the twist angle alpha I is the angle between the joint axis I minus 1 and joint axis I measured along the x direction, the xi minus 1 axis using the right hand rule. So angle between I minus 1 to I along the xi minus 1. The link length is the distance between the joint axis I minus 1 and I and measured along the again x axis of I minus 1 frame. And this is always a positive quantity. Now the other two are link offset. So link offset is measured along Zi and between xi minus 1 to xi. And this is basically a joint variable uh, when we have a prismatic joint. And in case of rotary joint, this is constant. And finally, the rotation angle theta I, which is the angle between xi minus 1 and xi, measured about the zi axis using the right hand rule. For prismatic, this is constant, and for revolute joint, this becomes the joint variable, right? And apart from these, like these rules cover the generally all the cases, but there are some special cases uh, in which the axes are oriented in a special way, like they are parallel or they are intersecting. And in these cases, we have some specific again special rules to handle them. So what we'll do here is we'll take a quick example, and we will find out the DH parameters for this system. This is the Stanford arm. Okay, so so first, before we proceed, we must note we must note that what are the degrees of freedom here in the system, right? And what are their types of joints? So we see that there is a revolute joint here, there is a revolute joint here, and there is a prismatic joint here. So this is what is a 3 degree of freedom RRP system. It is RRP system, and it's a 3 degree of freedom system. Okay. Now we will start assigning the frames. Right. So I'll just first draw the frames and then we can discuss. Okay. So I think we have most of the things that is required. So first, what we do is that we assign the base frame, and then uh, we start assigning the frames along the as per the DH convention. So first, degree of freedom is a revolute joint, and that is theta 1 that rotates about the vertical axis. So that I have assigned as z0, that is theta 1 about which it rotates, right? And then the other link is at 90 degree. So, but you see here that this z1, right, the axis of the first joint and the axis of the second joint, they are intersecting, right? So when they intersect, we can choose x-axis as any common perpendicular to both of them. Okay, so let's say we have chosen this as the x-axis, and since they intersect, the link length parameter is 0. So that is one thing. And finally, the third axis, that is this prismatic joint axis, right? That also intersects, right here. That also intersects. So basically, all three joint axes are intersecting. So Z2 and Z1 intersect here, and Z1 and Z0 intersect here, right? So all three joint axes are intersecting. So this should this what should we should conclude from this is that once the joint axis intersect, then the link length parameter, that is A, that becomes 0. Okay, so if we draw the tabular form in which we fill the DH parameters, right? So since all the all the joint axes are intersecting, the link length parameter, they're all 0 because all the joint axes are intersecting. Okay, then what we have is the twist angle, right? So twist angle, how did we define? We define as the uh, how is the joint axis changing about the x direction. So here, this is the positive x direction, x0. So uh, we take this. This is the x0 direction, and if we rotate, if we are to get from z0 to z1, then we have to rotate like this by minus 90 degree for z0 to z1, right? So twist angle becomes minus 90 degree. Then again, to get from z1 to z2 about the x1, we have to rotate, right? So z1 is like this. This is z1 and this is z2, and this is x1. So we have to rotate about here we have to rotate about like this in order to go from z1 to z2. Right, so this will be plus 90 degree. Finally, 0. Then this link offsets. So that is distance between the x axes uh, along the common perpendicular. So for first, it is d1 between x0 and x1. For second, x1 and x2, it is d2. And for third, x2 and the final end effector, that is d3. And that d3 is a joint variable, so that is changing basically. So d1 and d2 are fixed, but since it's a prismatic joint, right? So this is a joint variable. Okay. And finally, uh, for this joint angle, right? So for the first two, it's the revolute joint, so it's theta 1 and theta 2, and basically this is calculated by how x1 is oriented with respect to x0 along z0. So x1 if rotated, then it's theta 1 and theta 2. And then finally for the third joint uh, x2, and for the third joint, since it is not a rotating joint, that remains fixed, right? And along z1, that is, it is 90 degrees. Right. To about z2, we have to rotate by 90 degrees from getting to x2 to x1. So this sums up the TH table uh, for the stand this system. Okay, so that basically sums up the today's agenda. So if you have any questions, please feel free to ask them. Otherwise, we can wrap up here. Okay, then. Thank you for joining, and I will see you in the next week's discussions hour.